Welcome back to The Explainer. Okay, today in Episode 6.2, we're tackling a genuinely groundbreaking concept in electrical engineering. We're looking at Gabriel Kron's mathematical framework, better known as the Kron primitive machine. If you are someone who loves elegant, universal solutions to completely chaotic, complex problems, you are definitely going to want to pay close attention to this one.
Picture this. For decades, the absolute biggest headache for electrical engineers was dealing with entirely different, mathematically messy models for every single type of machine. I mean, induction, synchronous, DC, transformers, they all demanded completely different analytical approaches. The learning curve was incredibly steep, and simulations, well, they were a total nightmare. The field desperately needed a universal key, a way to answer the question, how do we model literally any machine with just one tool?
Well, Gabriel Kron actually found that universal key, and his answer was shockingly simple. He realized that you could reduce absolutely every machine down to just 2 perpendicular windings. That is it, just 2. And that one little trick completely revolutionized how we analyze electrical systems. Okay, let's dive into exactly how this works.
All right, moving into Section 1, the core 2-axis model, focusing on the direct and quadrature axes.
So building on some of the concepts from our earlier chapters, the Kron primitive machine represents stator and rotor windings along orthogonal, direct, and quadrature axes. We just call them D and Q for short. But right here is the absolute critical part. The rotor's windings are treated as quasi-stationary. What that means is they are mathematically frozen in place on the fixed DQ frame, even though, in reality, the physical rotor is actually spinning underneath it.
This is a brilliant move because it strictly separates our mathematical model from physical reality. Our analytical tool, the DQ frame, is completely stationary. It's frozen. Meanwhile, the real-world machine has parts spinning around furiously. By mathematically freezing that rotor, we completely eliminate all those nasty, complex, time-varying variables. It makes the calculations easily solvable across absolutely any machine type.
Let's move to Section 2, the 4-slot system, which acts as our universal building block. You can kind of think of this framework like a plug-and-play template, almost like an inventory in a video game. You have exactly 4 available slots. You've got the D-axis stator, the Q-axis stator, the D-axis rotor, and the Q-axis rotor. Building a math model for a real machine is literally just a matter of choosing which of these 4 slots actually get populated with windings.
What's really interesting to see here is how perfectly completely different machines map onto these exact same 4 slots. Take a DC machine, right? It needs a commutator winding on one axis. But an induction or synchronous machine, well, they populate all 4 slots, and they just differ in how the rotor circuits are handled. But at the end of the day, it's the exact same fundamental architecture, just populated slightly differently based on physical reality.
Okay, let's do a quick pause for Section 3, Quick Check, where we test the framework.
Let's make sure we've fully grasped this whole plug-and-play analogy. Here's a question to chew on. Which of the 4 Kron primitive winding slots does a simple transformer leave completely empty? Think about what we just learned regarding how physical motion dictates which slots get used. Got it? The answer is 2. Specifically, both of the rotor slots. And it makes total sense, right? Because a transformer has absolutely 0 relative motion. It just sits there like a brick. So it only ever needs the stator side D and Q windings. The rotor slots remain completely empty, meaning a transformer only uses exactly 2 of the 4 available slots. That makes the transformer the absolute simplest possible case of the Kron primitive machine.
All right, that brings us to Section 4, Summary and Next Steps, Preparing for the Matrix.
So the crucial point to take away from all this is understanding the Kron primitive machine as the ultimate universal template. 2 perpendicular axes, up to 4 winding slots. Absolutely every single specific machine in electrical engineering is just a particular configuration of this exact template. And this setup, it's the foundation for literally everything coming next.
Which leads us directly into our next step. Now that you have this visual, somewhat abstract template locked in, the next phase is turning it into actual, usable matrix mathematics. We are going to use this exact framework to formulate the impedance matrix. And that is a real game changer because it gives us the ability to solve for voltage, current, and power across any machine using one single unified equation.
Which leaves us with this final kind of mind-bending thought. If every single complex electrical machine out there, no matter how distinct or physically weird it is, can be elegantly reduced to just a simple 4-slot matrix using Gabriel Kron's brilliance, what other highly complex physical systems in our world are just out there,
waiting for their own universal template. Thank you so much for joining me on this explainer. Keep asking those big questions, and I will see you next time.